Hi everyone and welcome back to PrepFusion. I'm Anish and today we will start with the lecture 33 of DC generator characteristics. Okay, so all of the mostly the theoretical concepts has been done, right? Few numerical topics we had done initially while starting the DC machines chapter, and mostly the theoretical concepts has been done. Numericals also were there in in commutation, in your armature reaction. Numericals also were there for compensating winding and interpoles. So now also the next few topics will be the most important portion for gate point of view. Okay, so in between we had that construction and all those things. Those are not that important, but from now onwards please be fully attentive. Okay, these are very important topics for gate point of view. Previous topics of course are more important, but these are more important. Okay, so let's discuss about DC generator characteristics. What do I mean by DC generator characteristics? So what do you mean by characteristics? Characteristics are there to define how the machine behaves in different conditions. So characteristics basically means define the behavior of machines in different conditions. Okay, so we will vary our load, we may vary our field current, we may vary our resistance, we may connect a resistance and we may vary that. There are multiple ways where we can vary. So mainly there are three kinds of characteristics. So like one is the this magnetization characteristics, internal characteristics and external characteristics. So what we will do, we will plot the different values according to different uh, independent values. Let's say I am varying my field current. If I vary my field current, how is the generated voltage varying? Okay, so to in this lecture and next lecture we will discuss mainly about generators, and the lecture afterwards we will discuss about motors. So if I am varying my field current, how will my induced EMF or generated EMF will vary? That is what a magnetization characteristics, or also known as a no load characteristics, means. What is load characteristics? As the name suggests, if I am adding a load, that means load is connected. So in this case, right, assumption is my armature current is 0, or my load current, not armature current, sorry, IL will be 0. In this case, my IL will not be equal to 0. It will be some non-zero value where it will send the current, right? So it is internal characteristics and external characteristics and magnetization. So what is internal characteristics? Internal characteristics basically is the variation of the induced voltage with respect to the load current, and external characteristics is the variation of the supply, that is the output voltage, terminal voltage with respect to the load current. Okay, remember all these are done at constant speed and flux. Okay, we only vary the load current here, we only vary the load current here, and here as I am varying the field current, that means I am varying flux is varied here. Okay, but speed is constant. Remember here speed is constant, right, in this case, else I will not be able to measure the variation of induced EMF. Why? Because very basic formula we have derived, that my generated EMF Eg is equals to phi ZNP divided by 60, right? So if I am varying my flux and if I also vary my speed, right, I won't be able to measure what is the variation due to flux, because speed will also vary. So I can only vary only one variable here, so that I can quantify how does it depend, how that this induced EMF depend on the flux, right? So that's why I will keep the speed to be constant, I will vary my flux. So my induced EMF will be depending on flux. Okay, although it seems like here they follow a linear relationship, but you know, life is not linear, life is a sine wave, right? So it will not be that simple. That simple and easy. Okay, so let me discuss one by one with for a separately excited DC machine. So I will just give you a bit of overview. Okay, of course I will explain everything in detail, but initially I want to give you a heads up. So if I have a separately excited machine, that basically means what? If I have a separately excited machine, that basically means that, let's say I am plotting the first characteristics, that is no load characteristics, that is here no load is connected. If no load is connected, here IL is 0, so IL equals to IA only. So my line current is same as armature current, so armature current is 0. Okay, now if armature current is 0, there is no drop, so terminal voltage and the generated voltage will be same. But here I will have like this, right? Field circuit is independent of the armature circuit, so it will still generate some flux and still my armature is rotating. If it rotates, what will happen? It will induce a EMF, right? And an EMF will be induced, so it will be almost a like a similar, almost like a straight line. So here, right, in this case same thing, my E is equals to phi ZNP, EG will be equals to phi ZNP P by 60. So I can write here that EG will be proportional to phi. So if EG is proportional to phi, if I draw my magnetization characteristics, okay, if I draw my magnetization characteristics, my IF is varying and my this is my EG. So roughly it will be actually almost linear. Roughly it seems to be almost linear, but it will not be exactly linear. I will explain why. So why will it not follow a linear relationship? Because what am I doing? Actually, I'm connecting a voltage source here, and I am gradually increase the voltage, that is gradually increase the field current, and due to that increase in field current, gradually the flux is increasing. Correct? Right? But if your BH curve of this particular field, right, of this magnetic material is not a straight line. If it is straight line, that means what? That means it is a air core, right? Material is air core. Core is aired, right? Then roughly the graph will look something like this. It will just follow the straight line. Now you might have a question. So why does it start from here? So this point is known as residual, like this point of voltage is known as residual voltage. Why it is known as residual voltage? Because you know any magnetic material has some hysteresis. So even without any excitation, this will generate a magnetic field. Why? Because the north and south poles will already be aligned in this material, right? Due to hysteresis. We have discussed about this in transformer. That's why the hysteresis loss is there. So without providing any excitation, bit of magnetism will be present in the material. Hence, it will produce a magnetic field even without any field excitation. That is, IF, even if IF is 0, no field excitation, still it will produce some magnetic flux. And of course, I am rotating my generator. Remember, generator is always getting rotated with some constant speed, right? So if flux is there, generator is getting rotated with some constant speed, of course there will be some residual voltage. So this residual voltage is due to the residual flux. Okay, got it. Now what if the core is not air cooled? So of course there will be a certain point. If the core is not air cooled, there will be a point of saturation. What do I mean by saturation? So even if I keep on increasing my field current after a certain level, that is let's say 10 amperes, the magnetic flux will not increase. So even if I keep on increasing my voltage, that is the current IF, the magnetic flux will not increase. So the induced EMF also will not increase because it will become constant. So here also graph will be something like this. Okay. There will be saturation. Okay, here due to the core. Okay, got it. So this will be the roughly the open circuit characteristics. Don't worry, I will discuss about all the setup later on. I'm just giving you in one shot. If I want to plot the external characteristics or the no load characteristics, how will I plot it? Okay, now let's discuss about the external characteristics. So in the in the load characteristics, let's discuss about the internal characteristics first, that is Eg versus IL. Okay, so what is Eg versus IL? So if I just copy the graph, Eg versus IL. Now if the load current is varying, then what will happen? So here the assumption is that the field is constant and the speed is also constant. If the field and speed both are constant, what does it mean basically? So this is with respect to the load current, right? So if the field and speed both are constant, that means what? That means my Eg will be roughly almost constant, correct? If my field, like Eg is what? Eg is 5 Znp by 60A. So if my field and speed both are constant, Eg will be roughly constant. So if I keep on increasing my IL, the Eg will remain roughly constant, but there will be a catch. What is the catch? Catch is there is armature reaction, right? Because what will happen? Eg is constant, and if I keep on increasing my load, that is the load current will increase, right? If load current increases, the armature current will increase because here IL is equals to IA. If armature current increases, there is armature reaction, right? Due to armature reaction, what happens? Due to armature reaction, the flux gets reduced due to demagnetizing and cross magnetizing effects. So flux is reduced. Overall flux is reduced because the armature flux opposes the main field flux. So if overall flux reduces, this in turn reduces the Eg. Okay. So what will happen for lighter loads? You will not see this. For lighter loads, it will almost remain constant. For larger loads, what will happen? This will decrease. Okay. Now this gap is due to what? So the external field characteristics comes down due to armature reaction. Okay. So this is due to the armature reaction. Okay. So this is my Eg. So I will color my Eg like this. Now what is the this is the internal characteristics. Sorry, this is the internal characteristics. What is the external characteristics? So it's very simple, right? What is external characteristics? So what is Vs equals to? So in this case, our Vs, in this case, our Vs is equals to Eg minus IRA. So what will happen is if your armature current increases, although the here the Eg will be constant, but this IRA drop will increase. So further this graph will go down. The external characteristics will further go down. So the external characteristics will be something like this. There, of course, there will be armature reaction and additional drop there will be, that is due to the IARA drop, that is due to the armature winding drop. So in just one page, we simply have drawn the characteristics of separately excited DC machine. Okay, we did not need any extra things. Okay, so Yeah, so like same thing. What we do experimentally, we connect a external resistance, we vary the resistance. So although this voltage is constant, if we keep on varying this resistance, the field current will change, and accordingly the generated voltage will be there. Okay, very simple and easy to understand, not that difficult. So your no load characteristics when the load is not connected for a separately excited machine will be something like this, where these are few key points. So let me name the points OA, and let me name the saturation point, right? Saturation point, let me name it here. OAB. Okay, so what is OA? OA is the voltage induced due to residual flux present in the field poles. So OA, the voltage induced due to residual flux present in field poles. Okay, and AB is the basically saturation point. So B is the saturation point, right? This B is basically the saturation point. Okay, so yeah, I hope you have understood this very uh, basic point. Okay, so like of course I don't need to explain this graph, already we have understood this with our uh, like explanation in the previous page. Okay, and also we draw a straight line. So this line, right, this line is actually called the air gap line. This line is called as the air gap line. Why? Because if we had assumed the core to be air gap, then it would have been linear, right? But of course, like air gap has high reluctance, so it's not like like it is we are not using air gap, like we should use air gap then. No, air gap has higher reluctance, right? Core does not have, but core will saturate faster. So this is known as the air gap line. So this we also draw in the voltage characteristics as well. Okay, so yeah, I hope you have understood this basic point. Okay, okay, so like same thing is written here over here, whatever things I had discussed, same thing is written. A separately excited machine is one in which field winding is powered by an independent DC source and not same as the armature source that we will discuss in self excited machine like shunt and series machines. This gives us independent control over field excitation, making our analysis more easier and cleaner. So it allows us to study the behavior of the machine without interference from load or terminal variations. It gives clear relationship between flux, voltage and speed. Key ideas: since flux is controlled independently, we can observe how the terminal voltage responds to different conditions at constant or varying field levels. So one thing I noticed, due to armature reaction, the voltage waveform will shift now. It will always happen, right? Because the generated EMF will get reduced because the flux will be reduced, right? So this is the experimental setup. A rheostat will be placed in series with a field circuit to vary the field current IF. An ammeter is used in the field circuit to measure IF. A voltmeter is connected across the armature terminals to measure the induced EMF EA or terminal voltage VT. So these are the basically connections, right? If I show you, if I just take this diagram here, oh so okay, oh my god, what is happening? So if you see here, I have rheostat, here I have a, okay, where is the ammeter? Ammeter should, okay, ammeter also should be placed here, right? Forgot to place the ammeter. So ammeter also should be placed here. My apologies. So ammeter will be here. Okay, 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 okay. Okay, this is bad. Seems fine. Okay, so ammeter will be here. Okay, so this is the setup basically: voltmeter for measuring the voltage, ammeter for measuring the field current, and rheostat to vary the field current basically. Okay, so same thing. Open circuit characteristics shows the generated EMF EG varies with field current at no load and constant speed. So usually we vary it at rated speed only, like we use it at rated speed. It also reflects the, it essentially reflects the magnetization curve. Okay, so if we see that this was the magnetization curve of the machine, so it's almost similar to the magnetization curve because flux, if I vary flux, it is same as varying the magnetic field density, and if I am varying current, it is same as varying the field current, right? So here H will be proportional to IF and B will be proportional to phi. That's why it is just a reflection of the magnetization curve. This is known as the magnetization curve. That's why this curve is also known as magnetization curve. Okay, so yeah, those are the things that are written, that is written over here. So how do I find out this like open circuit characteristics? So initially there will be some linear increase because initially the core will operate in the linear region, then as field current increases we will operate in the saturation region, then after that what will happen, it will be just flat. For any increase in field current there will be no change in the flux density, so there will be no change in the induced EMF. Okay, so again, if let's say I would have made my flux to be constant, if I would have varied my speed, then similar kind of thing will happen. But now Eg will increase totally proportionally, right? Eg will increase totally proportionally. So if speed is increased, the open circuit characteristics will shift upward, and if speed is decreased, the open circuit characteristics will move downward. So same thing, let's write, let's say this is some speed n1. Okay, so if I am increasing my speed, so basically what will happen, the open circuit characteristics will shift upward because my induced EMF will is just proportional to the flux density, and if my reduce my speed, my induced EMF will shift downwards. Okay, n3. So this is how my speed varies. Okay, n1, n2, n3. Okay, so yeah, I hope you have understood this basic point. So basically ultimate point, key point to take away here is that my n2 will be the highest speed, n2 greater than, sorry, write this in white only. N2 will be greater than N1 will be greater than N3. N3 will be the lowest bit because there will be, that will develop the least amount of induced voltage. So same thing is written over here. Okay, how does my OCC change? Okay, so it will vary linearly. It will be just scaled linearly. That's it. Okay. Now few things we have not considered, like if it is at load, right? That I'm discussing about the load characteristics. So if it is load, if it is at load, and if I'm measuring the external characteristics, so I see there will be, of course, there will be a armature resistance drop. Also there will be a brush drop, right? Because current is flowing through the brush, so there will be drop due to that. Okay. So under load, Eg is always higher than V due to this internal drops. Even with zero load current, V may not exactly be equals to Eg because there can be a brush drop. So even if the load current is zero, we have assumed it to be almost equal to the developed voltage, but it cannot be equals to developed voltage also because there is a brush drop. Okay, generally it is 1 to 2 volts, so generally we neglect that. Okay. So no load characteristics is done when the load switch is open. So here, right, I will have a load switch and no load characteristics will be done. So I can draw the load switch when the load switch is open. Okay, so basically it will remain open and it will be closed only when we are discussing about load characteristics. Okay, so I can copy this diagram. Paste it over here. Okay, so whatever we have discussed, the same thing is written over here. What is the initial lineage and then what happens after that? Okay, how does the flux, there is some flux, residual flux, all those things have been discussed over here. Okay, so yeah, typically, so my no load characteristics, also known as the magnetization curve or the open circuit characteristics or the saturation curve. Okay, they can also call this all these three. Okay, so yeah, these are the things that we discussed. These are the key points. Whatever we discuss are written over here. Okay, I don't want to go through it over again because that will just waste our time, right? So load characteristics already we have discussed. So one more thing, that this open circuit characteristics is just like the DNA of a machine's magnetic, right? So first of all, this is a very important characteristics, and understanding this conceptually is very important to understand how the machine will behave, right? It tells you how much EMF the machine wants to generate at certain excitation. But what you actually get at the terminals depends on speed, brush drops, and internal resistance losses. Okay, all this depend on that. Okay, so that's why understanding the open circuit characteristics is very important. Yeah, coming to load characteristics, just one slight mistake I had made here. That was my mistake where I was explaining. So this load characteristics, right? It has two types of characteristics. One is EG versus, it is not IL actually. That was my mistake. Here it will be EG versus IF. Okay, slight mistake on my behalf. This will be EG versus IF. So here, right, actually in the internal characteristics we will vary the flux. The load current will be constant. So bit of mistake on my behalf. In both the cases, load current will be non-zero, right? In both the cases, load current will be non-zero, but in the first case, the speed will be constant and the load current, that is IL, will be constant. Okay, in this case the speed and flux will be constant. So these are the cases. So here bit of mistake on my behalf. So right, this is not the internal characteristics. This is just a characteristics, does not have a name. This is the external characteristics, right? And now I will draw the internal characteristics. What will happen? This is the external characteristics. Okay, so now I will draw the internal characteristics. What will happen if my load current is there? Okay, so sorry for the mistake, माफ कर देना, ठीक है, क्षमा क्षमा प्राप्ति हूँ मैं. तो now let's start with the load characteristics. Okay, external characteristics is pretty easy to understand, but maybe internal might be a bit difficult, right? So here, right, what we are doing, same experimental setup, that I will vary my field current and I will measure the voltage, but this time remember there will be bit of armature drop because this switch is closed. So this IA is equals to IL, IA equals to IL, which is not 0, which is not equal to 0. Okay, IA equals to IL, which is not equal to 0. So what I can say, is that there will be some drop here, right? So if some flux initially it will have, and it will generate some voltage, that will be known as the residual voltage. But remember, I won't be able to pass on any current. Why I won't be able to pass on any current? Because I have told you, right, now the generated voltage, as the load current is non-zero, it has to both overcome this armature drop, right, and whatever and the brush drop. If load current is not zero, if load current was zero, then there was no problem. This was my no load characteristics, right? This was my no load characteristics. If load current is if load current is non-zero, what will happen? The graph will simply shift down due to what? Due to armature reaction and the IARA down. I have already discussed, right, how the graph shifts down. So graph here will shift down. It will shift down somewhat like this. So even with some field current, I will not be able to generate any voltage. Why? Because there will be some drop in the armature resistance and the brush, right? I have to overcome that drop, then only I'll be able to supply any power, then only the IA will be not equals to 0. Okay, so for me to supply any power, right, so what do I mean by it is, actually they will yeah, I have to overcome these two drops, right? Otherwise how I will be able to supply the power? That is, what do I mean by it? Let me take few examples. Let me take IA, armature current equals to 1 ampere. If armature current is 1 ampere and there is some load connected here, okay, so it has to take 1 ampere of current. So first of all, there will be drop here and drop across the brush, then only I will be able to supply the 1 ampere current, because it has to generate enough voltage so that 1 ampere current flows, right? Let's assume that overall path, right? So basically what do I mean is, okay, let me draw the circuit. So here I have EG, and here I have, let's assume, an armature resistance of 0.1 ohms, and of course there will be a brush drop, right? If load current has to flow, there will be a brush drop of, let's say, 1 volts. Then there is a load connected. Okay, let me assume it to be 10 ohms. Okay, and I want my current to be 1 amperes. Okay, I want my current fixed to be 1 amperes. What value of EG will make it 1 amperes? So if I assume there is some residual flux, due to that residual flux, there will be some residual voltage generated, and let me assume that residual voltage generated, EG, to be 1 volt. Is that sufficient to pass 1 amperes of current? No, that is not sufficient to pass 1 amperes of current. Okay, so Yeah, that is what I wanted to uh, discuss over here. Okay, so I hope you have understood this basic point. Okay, so load characteristics actually here, right, it includes, actually again I'm bit wrong here. Okay, again I made a mistake. This, right, is not with respect to Eg versus IL. This is actually with respect to Vt versus IL. Okay, I'm sorry again. I'm again sorry. This is with respect to Vt versus IF. Okay, not Vt or Vs, the terminal voltage. Instead of writing Vs, it will be better if I write Vt, right? The confusion will be less because supply is something else. Okay, I hope it will be more clear now. Okay, yeah. So this was the internal characteristics. Now I will discuss about it. So yeah. So I hope you have understood this point. If due to the residual flux I have the generated voltage as 1 volt, but it is not sufficient to provide 1 amperes of current. So what will happen? I have to increase my field current further so that Eg increases further and so that 1 amperes of current flows. But remember, if I increase my field current further, flux will increase further, and slowly there will be some amount of current. Ia will increase. Let's say Ia increases. Currently what is the Ia? If I see, currently Ia is 0. If let's say the Eg value is 2 volts, 2 minus 1 divided by 10.1, right, roughly it will be equals to 0.1 amperes. Roughly it will be equals to 0.1 amperes. So roughly if it is equals to 0.1 amperes, then again Ia will increase. If Ia is there, then there will be armature reaction. There will be armature reaction. If there is armature reaction, what will happen? It will further reduce the flux. So Eg will reduce again. So I have to compensate for that. I have to further increase my field current further, right? Further and further. So that is what we will do. So Eg, right? Eg, if I draw the Eg graph in blue, Eg will be almost similar. If armature current is there, basically I will have some residual amount of flux that will still be starting point will be still same, but this time as the armature reaction is considered, what will happen is that it will be starting below the graph. So armature reaction will be considered and IARA drop will be there, right? So this will be the graph for Eg. Okay, and this is not the internal characteristics, please remember it. This is not the internal characteristics, this is just the Eg. So here only the armature reaction is considered because I am plotting Eg, and Eg is dependent on armature reaction. It is not dependent on IARA, right? IARA drop, because it is Eg, right? Internal here. Okay, so previously whatever I was saying, just a mistake on my behalf, because it is internal characteristics, because here the I am varying something internal there, right? I am varying the field current that is internal to the machine. That's why it is named as internal characteristics. Okay. Overall, it is a load characteristics because we operate it at load. So there is some constant load current. So if I am plotting only with respect to armature reaction, then this will be the graph of Eg. Okay. Okay, sorry, if armature, so this also, sorry, this also will shift down, right, because the initial residual flux also will reduce its value due to armature reaction, because armature reaction further will reduce the residual flux, right? So this is the value of Eg. Now if I further consider the drop of IARA, that will be the actual load characteristics, right? Okay, please ignore whatever I have said previously. I'm sorry for the mistake. So now remember this thing, that I will not get, I have to provide at zero field current, right? There will not be any terminal voltage, because okay, there is no load current, but there will be some sort of terminal voltage, right? Yeah, there will be some sort of terminal voltage still. But if my load current is not there, basically we will ignore this portion. Our graph will start, this will go down further. Yeah, this will go, it is at a constant load current. If it is at a constant load current, that means basically what will happen, ideally what will happen actually, the graph shifts down. Okay, So whenever there is some load current flowing, this drop will be very very higher than the residual value. Okay, this is the actual, this is the residual voltage without any armature reaction considered. If I consider armature reaction, the residual voltage will further shift down, and if I consider the IARA drop, the residual voltage will not be sufficient to flow any current. Why? Because basically this brush contact drop will be higher and all those things will be higher. So if the residual voltage is assumed to be 1 volt or 0.5 volt, there will not be any current, right? So there has to be a minimum amount of field current that will let the circuit to work. What do I mean by it? So if I assume here that my brush voltage to be 2 volts, if I assume my brush voltage to be 2 volts, then what will happen? Then if I assume my residual voltage to be 1 volt including armature reaction, will any current flow? No, no current will flow, right? So this value is the point, this point is the point where I will keep on increasing my field current, and after a certain stage what will happen, there will be some finite value of current, right? I will get a terminal voltage. Otherwise, if there is no I will not be able to overcome this brush drop, right? So ultimately at the output I will not get any voltage. Okay, I hope you have understood this point. So from this starting point, this is known as the IF minimum, that is the minimum field current required to overcome the brush drop and the armature reaction and the although IRA won't flow, but to overcome the brush drop and the armature reaction. Okay, so minimum field current required to overcome brush drop and armature reaction. Okay, yeah, so that is the case over here, and this is the actually, this is including the IARA drop, right? This is armature reaction only, IARA plus the brush drop. Okay, so here this is actually the internal characteristics. Okay, very important and key point to understand. Okay, so important point to understand, between no load characteristics and load characteristics there are mainly two drops. One is armature reaction and another one is IRA plus brush drop. Okay, so yeah, that was about the load characteristics. So here same thing whatever we discussed. So here, right, again circuit diagram will be same. Here the external resistance will be connected here, so we will only vary our field current. Okay, and the switch will be closed, so there will be a constant load connected. Let's assume that I am connecting a constant current source at the output. I DC. Okay, constant current source is there, due to which I'm already plotting the graph. Okay, So same thing is written here. Now the load is connected, switch is closed. Initially IF is varied via rheostat. So via rheostat will vary the IF, which causes changes in EA. To isolate voltage behavior, IA is held constant by, like, then we will yeah, so we will, like, here we have connected a constant current source, but we can make IA constant in different ways. So here they have done something else. By adjusting the load also, you can make the IA, the armature current, to be constant, and the corresponding terminal voltage is noted. So there are mainly two drops. One is the IARA drop, armature reaction drop. Effective EMF will be due to the IARA, and the drop due to the armature reaction. The load characteristics lies below the open circuit characteristics. So open circuit characteristics will be lying at the top always. This is the no load characteristics, or also known as the open circuit characteristics, right? And the load characteristics will lie below it. Okay. The x-intercept of the load curve shows minimum IF required to overcome the combined effect of armature reaction and IA. Okay. So this x-intercept of the load curve right here, x-intercept, this tells me the minimum value of IF that is required to overcome the brush drop and armature reaction. Okay. IARA drop is not actually correct, because anyways current is not flowing. So how can I overcome the IARA drop? So it is technically incorrect. Only the brush drop and the armature reaction we will overcome. If some current flows, then only there is some brush drop, right? So yeah, those we will overcome basically. Okay. So yeah, this was the internal and load characteristics. So in internal and load characteristics, what we do, again the same thing, that we vary our flux. Flux is varied, and our speed and load current is constant. Okay, this is the important portion that you have to remember. Same thing is written over here. I don't think there is something different. Now let's discuss about the external characteristics, which we had already uh, discussed, right? It was very simple, like, which I had drawn first, but I mistakenly drawn it as a internal load characteristics. So this will be the external load characteristics, not that difficult to understand. This we had already discussed previously, so I am not repeating the same thing, right? So here the load current will vary, the flux and all those things will be constant. So if flux is constant, there will be armature reaction, correct? So whatever we had discussed previously, those things will be there. Let me, okay. Okay, so yeah, I hope you have understood this basic point. Yeah, plots the variation of the terminal voltage. So this is the variation of the terminal voltage. This will not be Vs, this will be the terminal voltage with respect to the load current. Okay, so here also this will be the terminal voltage. Okay. Okay, so yeah, that is what we have discussed. External characteristics are determined experimentally by connecting a voltage source or something. So this time the experiment will be here, right? The circuit diagram here, instead of a rheostat being connected at the field, there will not be any rheostat connected at the field. Okay, so how do I, yeah, I can draw the circuit over here. There will not be any rheostat. There will be, basically what will happen, there will be a rheostat connected at the load basically, an ammeter also. So this is the, this will be the value here. Ammeter should be here, right? Okay, so we will vary our load like this. R external, this will be constant, this will be constant, only this will get varied. So very easy and simple to understand. So terminal voltage drops are due to these two reasons. It is used to determine the voltage regulation, stability of supply voltage, and suitability for parallel operation. Okay, so if I see, although here I am exaggerating the drop will be not very high. So generally we use our separately excited machine for where wide range of output voltage is required. If my range is very high, if my load is varying very much, right? So basically, if my load, if load varies very much, and I want my output voltage also to vary very much, right? Because I want my output voltage, I want more range, more range of output voltage. If I want these things, I may use a separately excited machine, because this separately excited machine will give me more range, although the reasons are different due to armature reaction. So it depends what kind of load you are connecting, in which situations you use. So that's why these are important to understand where to use what kind of generator or motor. So that's why these characteristics and graphical explanations are very important to understand. Okay, so quickly I want to uh, like summarize whatever we have discussed. So this, for a DC generator, we had discussed about the case where what was varying, where my I was measuring the generated voltage versus the field current, right? So what things are constant here? The things that are constant here is the speed, and my load current is 0. So that's why this is called as the open circuit characteristics or the no load characteristics. Okay, next up we have our uh, load characteristics. So load characteristics is with respect to Vt versus If, where the, so this is constant, I forgot to write, this is constant, speed is constant, where the speed and IL is constant, where the speed and IL is constant, and what I can say is, my IL, sorry, speed and, yeah, IL is constant. My I'm varying my IF, and it is non-zero basically. IL is not equal to 0. That is also another condition. So that's why it is called as the load characteristics, or also called as the internal load characteristics. Next up is the external load characteristic, that is the Vt versus IL. If I vary my IL now, so now my speed will be constant and my flux also will be constant, that is the field current also will be constant. So this is known as the external load characteristics. Okay, there is another kind of characteristics for a DC generator. Yeah, the fourth one actually is the same one only, that is the like this external load characteristics, also known as the armature characteristics or load regulation characteristics. Why load regulation? Because it measures how the voltage, external voltage varies with respect to change in load, right? So the fourth one actually is the same one only, this one. Okay, this Vt versus IL. So load regulation characteristics. Now we will discuss about shunt generator, because like questions will not be asked from separately excited. This was just to understand what characteristics are. Okay, so now let's discuss about the shunt generator. What is a shunt generator? So let me put the picture of a shunt generator here, right? If it is a picture of the shunt generator, what will happen in a shunt generator? What will be the open circuit characteristics for a shunt generator? Okay, that is what we want to determine, right? So here what I can comment, what I can say is that if my like what is open circuit characteristics, where load current is not there, so Is or IL equals to 0, right? This is 0, so my IA armature current will be the field current, right? Armature current will be the field current. Now the thing that we discussed previously, right, that there has to be some residual flux that will generate the voltage. Now what we will assume, previously in separately excited machine, when we were plotting the load characteristics, the internal load characteristics, I told you that the residual flux was not enough to overcome the brush drop, right? It was not enough to overcome the brush drop. But here what we will assume, because even though there is no field current, even if let's assume that there is no field current, there will be some residual flux here, and due to that some voltage will be induced, but that will not be enough for the armature current to be equals to non-zero. There will not be any field current because that will not be able to overcome the burst drop and the armature drop to flow some current, right, as we had discussed previously. So same thing, there will be some, like even if the armature current is 0, why is it 0? Because there is no load connected, and if there is no load connected and it is this is a self excited machine, and for armature current to be not equal to 0, what needs to happen? Whatever residual in EMF it will have, it has to be more than the armature reaction drop and the IARA drop, right, for some current to flow. I mean basically it has to be more than the armature reaction drop and the brush drop, correct? So which I don't know, if some current will flow. So IA will be 0. Why? IA will be 0 because there will be a residual flux. Due to that, a residual induced EMF will be generated in this armature. My circuit will be like this, right? This will be the field coil, this will be the armature resistance, this will be the E residual. Now you might say, sir, there must flow a current. No, there will not be any current. Why? Because a opposing voltage drop will be there. Basically, what is that opposing voltage drop? Armature reaction plus brush drop. So this opposing voltage drop will be there, that is the armature reaction plus the brush drop. due to which even though there is some residual voltage, but current will not flow because automatically it will oppose it. So automatically it will nullify it. So here IA will be 0. IA will be simply 0 because this E residual will be nullified by the armature reaction and the brush drop. Okay, so no current will flow through here. Okay, no current will flow through here. So the field current is 0. But haven't I told you, even if the field current is 0, still there will be some residual flux, right? That is totally valid. There will be some residual flux. Due to that residual flux, there will be some generated EMF. So EG will not be equal to 0. EG will not be equal to 0. It will be equal to E residual. But current will be 0. Okay, that is the important portion. Current will be 0. Okay. Now what happens in case of a shunt machine? What will happen in case of a shunt machine? So I have discussed that if my residual voltage is lower than the, so this was the case 1. What is the case 1? Case 1 is the case for which my generated residual voltage is lower than the armature reaction plus brush drop. If it is lower, right, if it is lower, then no current will flow, and if no current flows, the flux remains phi residual and it does not vary. So basically my residual voltage is less than the brush drop and the armature reaction. So if this is the case, that means my armature current and field current both will be 0. So my flux never changes. So flux is constant. So if flux is constant, that means my EMF generated will also be constant. It will not change. So basically here in this case, EG will not change. EG will not change. Okay. EG will not change, and we give it as the term as voltage buildup has been failed. So what do I mean by voltage buildup? That we will learn in the second case. So in this case, the voltage buildup has failed. Okay, so in this case the voltage buildup has failed. In the case 2, I will assume that whatever is the residual voltage that we generate is greater than the armature drop and the brush drop, so that there will be some current flow. So if it is more, right, if it is more than the drop, what will happen? Initially, as soon as I will close the switch, let's assume that there is a, like, it is open circuit, load is open circuited, so load circuit is totally open, no problem. Load circuit is open, and field circuit is initially open, right? This will be open circuit. And this I will close. So as soon as I close it, assumption is that there is enough residual voltage. Now if I draw the equivalent electrical circuit, right, so electrical circuit will be somewhat like this. So there will be the resistance RA, there will be this opposing voltage, that will be the armature reaction plus the brush drop. Okay, although I am just showing the electrical equivalent, actually it is not a voltage drop, right? Actually it is a flux, it opposes the flux, but I am just showing the electrical equivalent circuit diagram. There will be the armature reaction, and trust me, no one will explain you. You go and search anywhere, just search the open circuit characteristics of shunt generator. No one will say you this, no one will explain. I am giving you the intuition. Everyone will start directly. Everyone will start with case 2 directly, voltage buildup. You can go look at any lectures around YouTube, anywhere, right? Any paid course, anywhere you go. No one will explain you this, what I am explaining you. Okay, so this armature reaction and brush drop is there, and then there is this residual voltage. And what we have assumed that our residual voltage is more than this drop. So what will happen if it is more than the drop? then there will be some current, that is IA, that will be equals to IF only. So what will happen if IA is flowing? So what is happening? IA is not equal to 0, that is IAF is not equal to 0. So residual flux was getting generated when my phi residual was getting generated when I had no field current. But now IF is non-zero. If IF is non-zero, then my flux will increase. If flux increases, then my EG will increase, because EG is dependent on the flux. So if EG increases, what will happen? The IA will try to increase, and remember there will be drop in the resistor as well, right? An armature reaction also will be there. IRA drop plus the armature reaction also will, this drop will also increase. So overall the voltage will increase, but not, I mean, to infinity. It will reach a steady state point. What will be the steady state point? That is what we will discuss, right? What is the steady state point? Here the steady state point will be the point at which both it coincides with the RF line. So if I assume one thing, that the field coil resistance is RF, and if I assume that generally it is a shunt resistance, right? So shunt resistance is very higher than the armature resistance. So you will see practically as well that your field resistance, shunt resistance, will be 150 ohms, and your armature resistance will be some 0.1 ohms, okay, even lower than this, okay. Or like in the questions you will see, okay. So initial field current will be E residual minus, of course, whatever drops were there, E residual minus the armature reaction plus brush drop divided by the RF plus RA. Let me write this RF in capital. Roughly I can write it. I can roughly, armature reaction and brush drop will not be very high. If I assume like it will be roughly like 10 volts, and let's assume that E residual, in this case E residual, if I assume it to be very high, okay, if I assume it to be like, okay, let's not assume it very high, let me keep these values, okay, otherwise you will get confused. So it is E residual armature reaction plus brush drop divided by RF only, because RA is almost negligible. So a steady state, what will happen? So a steady state, at a certain stage they will coincide. What do we mean by coincide? So slowly my generated EMF will increase. So if generated EMF increases, the field current also will increase, because the armature current will increase, so the field current will increase, so the flux will increase, right? And at certain point both of them will coincide. What do I mean by coincide? Basically I have a characteristics, right? Field characteristics EG versus the current IF. So it, if you remember the magnetization curve, this was the magnetization curve, right? And what is happening, initially I have residual voltage, then it is increasing here, then it is increasing here, then it is increasing here, then it is increasing here. So what will be the steady state? Steady state will be, basically, if you remember one thing, that what is the field current equals to? Field current is equals to EG minus whatever the extra drops divided by RF. So if we see that IF is dependent on EG minus drop divided by RF, so it is just a straight line with slope 1 by RF, right? Straight line with slope 1 by RF, or sorry, straight line with slope RF actually, because if I want to write EG in terms of, so if I want to write EG in terms of IF, so it will be IF into RF plus drop. So basically this will be the line. So ultimately what is happening is, where this is the line with slope RF, okay, where these two lines will coincide. So this voltage build up and this line will coincide. Actually, although they don't, here you are seeing they are coinciding here, actually officially they will not coincide here. Roughly the values will be somewhat like this, okay. Let me make it more better, otherwise you will get confused. So roughly this will be the value. So how is the voltage build-up process happening? So this is the straight line which says that my IF current has to follow this equation, right? At steady state, IF will be equal to this value, correct? Eg minus V drop by RF, correct? So what will be the steady state value of Eg? Steady state value of Eg will be IF RF plus drop. Wherever this graph, this line, this straight line and this Eg graph, what is the Eg graph? Eg graph is something like this. So initially there was some residual flux due to some residual voltage was there, some current flow due to the current. So now IF has increased because IA has increased. So if IF has increased, so basically it will lie somewhere around here. It will lie somewhere around here, okay. Then as IF has increased, so my generated voltage also will increase, and this will keep on happening, right? This will keep on happening. Although here you might seem that this graph is coinciding, it is not actually coinciding, okay. This will keep on happening, like this will again increase, this will again increase, this will again increase. Like if my IF increases, so my EG will increase. If my IF increases, so my EG will increase. So at a certain stage what will happen, because if my EG has increased, it has to follow this equation, right? KVL. If my, let's say, okay, what do I mean? Let's take few numbers. Let me take few numbers. So initially, let's say I started with 1 volts, right? E residual to be 1 volts. If E residual was 1 volts, and let's assume that the armature reaction drop are 0.5 volts and RF is, let's say, 1 ohm. Just taking an example, okay? So right now what is the current? Current is IA, that is 0.1 minus 0.5 divided by 1, that is 0.5 amperes. What is that? That is field current. How did I calculate it? Using this equation. What is this equation? Same equation as this, right? So it has to touch the straight line because I have to follow the equation, okay? I have to follow the equation. So that's why the IF value will be corresponding to this equation at this point. So the IF value, increase in the IF value will be like this. Then suddenly after I reach this point, what will happen? As the IF has changed, IF has increased. If IF has increased, phi F will increase. If phi F increases, the voltage will increase. The voltage will increase according to the magnetization curve. So this is the magnetization curve, right? Because it depends on the flux. So this is the magnetization curve. Okay, so this is the magnetization curve, and this is basically the voltage build-up process. Okay, so again, if the voltage has increased here, Eg, again I will calculate my Ig according to this equation. Again I will calculate my IF according to this equation. Again I will calculate my IF according to this equation. It will be Eg minus drop divided by RF. So again IF will increase, right? Because Eg has increased now. As Eg has increased, so IF will also increase. Again the IF will come here because it has to follow this equation of straight line. So IF will come here. Again is IF has increased. So again Eg will increase, and this will keep on happening until there will be a point of intersection where both this graph and the magnetization curve will coincide. If both of them coincide, both are satisfying. So previously there was conflict. There was conflict between this straight line, between this straight line and the magnetization curve. But here the conflict has resolved. So if previously this straight line was saying 1 ampere of current should flow, according to 1 ampere of current, the Eg value should be 10 volts. But the magnetization curve was saying if IF is 1 ampere, then Eg should be 15 volts, right? There was conflict. But at this point, the conflict got resolved, okay? Just like the conflict between your partner, right? So here the conflict has been resolved. How can you resolve the conflict? So either you agree that whatever she said was correct, okay, that's how you resolve the conflict. You just agree whatever she said. If she said that it was your mistake, it was your mistake, okay. Just joking, don't take it seriously. So that's how we resolve the conflict. Both of them agree at a certain point. So here the intersection point is known as the point of agreement, okay. Intersection point is known as the point of agreement. Intersection point between the magnetization curve is known as the point of agreement. So here the conflict got resolved, so there is no problem. If field current is 10 if field current is 50 amperes, or like not very high, if field current is 20 amperes, the voltage should be 150 volts, so as the magnetizing curve also saying the same thing, okay. So this was basically the voltage buildup process, okay. And trust me, you go anywhere in YouTube, anywhere in paid course, anywhere, no one will explain like this, no one, okay. So yeah, okay, so that is a very basic thing whatever we have discussed. So this line is the air gap line basically, and this is the magnetization curve. So magnetization curve we already know. So magnetization curve gives me the relationship between Eg and flux specifically, okay. Eg and flux relationship is drawn over here. This I don't need. And the field current line is drawn over here. Although this will be somewhat like this actually, because initially, okay, like I will draw it bit properly because you will get confused otherwise. Okay, so now how will the voltage buildup process be? So here initially there will be some current, delta current, some voltage will be there, again a delta current, voltage, like this it will keep on going on, right. So like at this point what is happening, so if I start from here, so initially there was no field current, so this was the residual voltage, right, E residual. So as soon as there is some E residual, and assumption is that it is more to E residual is more than the armature reaction and the buildup, so some current will flow. So as soon as some current flows, what happens? As soon as current flows, so the field current is not zero anymore, field current is here, let's say 0.1 amperes. As soon as the field current is 0.1 amperes, then according to the magnetization curve, we got to know that the generated EMF will be higher. So the generated EMF will be here according to 0.1 amperes. So if the generated EMF is higher, so Eg increases, so my armature current will increase, so my field current also will increase, it will reach here. Again this will go on, go on and on, go on and on, okay. There is a song, go on and on, okay. So this will happen, and this will keep on increase until this point, until this point where both of them will agree, where the conflict will basically be finished. So this is about the voltage buildup basically, okay. I'm not discussing about the terminal voltage for now because there is no load connected here. So terminal voltage will be basically, if I want to measure the terminal voltage, if I don't want to measure the Eg, if I want to discuss the terminal voltage, it will just be the extra additional drop of IRA. So the graph, right, will further shift down by IARA. That's it. Graph will further shift down by IARA. Nothing else will change. Okay. So this process, right, it takes a bit of time. It does not instantly go to its steady state voltage. This procedure is known as voltage buildup in DC shunt machine. Voltage buildup. in decision machine. Okay, so it takes a bit of time. Okay, so Vt will be just the extra additional IARA drop. All this we have discussed using the armature reaction drop as well. Okay, like Vt just it will be shifted downwards. So if my graph is here upwards, it will just be shifted downwards. So can duplicate this value, it will be just shifted downwards. This will be the extra additional IARA drop. Okay, so that's it basically. That's how you do it. That's how you do it. So I hope you have understood. So whatever we have discussed, the same thing will be written over here. Consider a basic DC machine. If you take its field winding and connect in parallel, there is a key difference from the separately excited, where the field gets supply from an independent DC source. Here, how we compare, the field winding is in series with the external field rheostat. So actually the circuit diagram is something like this. So it is connected in series with the external field rheostat. So as it is connected in series with the external field rheostat, if the R external is very high, if it is very high, then the current will almost be zero. So only the residual flux will be generated, because there will not be any increase in current. So that was the case one, right? If I assume my R external, to be very high, okay, infinity. So what is my IF current? IF current is simply Eg minus all the armature reaction plus the brush drop voltage divided by the R external plus R. Previously I did not discuss about R external because I was not discussing about the experimental setup. Here actually what we do, that is what I am discussing. So R external plus RF. So if my R external is very high, then this will be roughly almost equals to 0. So here, right, only my Eg will not vary. Eg will be equals to E residual. Eg will not change because IF is not changing. But if I keep on slightly reducing my R external, what will happen? IF current will increase. If IF current increases, basically the Eg will increase. If Eg increases, IF will further increase. So this is just a positive feedback. Positive feedback. Okay, just like a positive feedback. So here what they have done. So here's how we configure a shunt generator. The field winding in series with the external field rheostat is connected. The machine is mechanically driven at rated speed. So slowly the R external will reduce and the voltage buildup process will happen. Okay, so like if for the students who don't know, that if armature current is 0, then like field current will be 0, then they will assume that there is no flux, so flux will be 0, then Eg will be 0. But we have already decoded it that there will be residual magnetism. That's why we studied this residual magnetism in separately excited machine. So residual magnetism will help in initially generating some voltage, and slowly the build-up process will happen. So the residual flux generates Eg. The Eg causes a small IF field current. The IF produces additional flux, thereby increasing the total flux. Thereby the Eg is further increases, and this leads to more IF, and this cycle continues. This positive feedback loop causes the terminal voltage to build up gradually until it reaches a stable operating point determined by the field circuit resistance, right? Because like initially I was just showing you the experimental setup that RF is connected, R external is connected here, but whatever is the resistance here, determined by that, it will, the final steady state voltage and current will be determined, right, for no load characteristics. Okay, So it is the intersection of the magnetization curve, magnetization saturation, and the field resistance line. Okay, so it is the it is the intersection of it is the intersection of the field circuit resistance and magnetic saturation. Okay, so yeah, I hope you have understood this basic point. So whatever we have discussed, the same thing is written over here. And yeah, stable point, how do you determine the stable point of open circuit characteristics? That is what we have discussed, right? So yeah, I hope we don't need to uh, like discuss this much. Now there is one concept known as the critical resistance and critical speed. What do I mean by critical resistance and critical speed? So if I bring this graph here, right, if I the graph that I have drawn, if I copy this graph and paste it over here, so what can happen if, so this slope is my field shunt resistance slope, let's say R1. Okay, and if I increase my R1 further, what will happen if I increase my R1 further? So the slope will be further higher. So this graph, this straight line will rotate in the anti-clockwise direction for the right. It will be rotating somewhat like this. So what happens is that, let's assume that this point is basically R2. Okay, and this point, so if I increase, right, here the stable point has changed, right? And if I keep on increasing my resistance, if I keep on increasing my resistance, that is my resistance, if I keep on increasing, what will happen? After a certain stage, this graph will be tangent to the magnetization curve. Okay, so let me color this. So let me delete this voltage buildup. This is just basically distracting. R3. Okay, so what is happening? It is just tangent to this, right? It is just tangent to this. So there will be certain point, it will not have any stable operating point, because after this, right, after this it will, like if I am at this point, how will the voltage buildup look like? So let me draw the voltage buildup. If the resistance line is tangent, the resistance line is tangent, how will the, okay, how will the voltage buildup look like? So let me, okay, how can I delete it? Very risky. Okay, not this, very risky. Okay, this I will not be able to delete actually. How will I delete it? Oh my god. Oh, okay, yeah. So basically, if I see the this graph, so again writing down numbers here, so my R3 is higher than my R2 than my R1. So now let's discuss about the voltage buildup process, how the voltage buildup will happen if my R3 value is this, which is tangent to the graph. So let's take the case of E residual. Okay, so what is the equation? Equation of current, field current, IF. IF will be E residual minus whatever is the armature reaction drop minus the plus the volt brush drop or whatever external drops there are divided by R3, right? So it has to follow this line, it has to follow this equation. So it has to follow this equation. What is this equation? This equation is basically this equation of this line, right? It is the slope here. Okay, remember this R3 is the slope here. This R3 is the slope. Okay, so it is basically the equation of this line, correct? It has to satisfy. So where does it satisfy? It satisfied. So what will be the increase in IF? Increasing IF will be something like this. It will be a sudden jump. It will directly reach at this point, because only at this point, not at this point, only at this point they are touching, right? So it will directly reach this point, because before this there is no other place where the IF, like basically the this graph, this line can, this bottom line, like there is no other place where this graph is at the top or in the base. So if you see in the previous cases wherever we are discussing about the voltage buildup, so this graph was always in the top, right? So there was enough voltage for some current to flow, correct? Always, you see, always there was enough voltage for some current to flow. This was the direction, right? This was the direction of the flow, like this, like this, like this, like this, like this, like this. Okay, so this was the direction of the flow. So if this is the direction of the flow, then graph should always be whether equals to this line or above the line. So only one point is there. If the slope is tangent, only one point is there where the graph is equals to the magnetization curve. So directly I will jump in this position. So directly the field current will increase here, and directly due to the increase in field current I will reach to this steady state point. This will be the value, this will be the EG value, right? Steady state, EG at steady state. Now what if my slope increases further? What if it is R4? So if it is R4, if it is R4, what do you see? If it is R4, let's say if R4 is higher than everything, right? R4 is here. So will these two graphs ever touch? So it's basically like uh, like there is a topic that has no conclusion. Okay, so like you are in argument with your like partner, and there is no point of conclusion. So either like there is a discussion that this film was either good or bad. So you said it is bad, your partner said it is good. So there is no point of intersection. So same thing, right? There is no intersection. So there is no intersection here, no intersection. So if there is no intersection, right, this equation will never be satisfied. This equation, if I change this to E residual minus armature reaction plus brush drop divided by R4, never satisfied. So no intersection. So if there is no intersection, then voltage buildup will fail. No intersection, voltage buildup will fail. Okay, so that's why if my resistance of the shunt is more than the critical resistance, then there will not be enough flux to accumulate the voltage buildup. So voltage buildup will fail. The limiting value is the known as the critical resistance, that is the tangent to the open circuit characteristics. Okay, not from the origin, actually it depends from the origin. If I assume from the origin, if I neglect the armature reaction and the brush drop. So if I neglect the armature reaction and brush drop, what will happen? Can you say if I neglect the armature reaction and the brush drop, what will be the open circuit characteristics? The open circuit characteristics simply will shift down. Okay, everything will start from here. That's it. Everything will start from here. That is the open circuit characteristics, basically. Very simple. Okay. So yeah. Now what is the critical speed? Again, if my speed is less than the critical speed, then the voltage buildup will fail. So if it is below, right, what will happen? In the initially, if I have discussed you, there are two ways, right? There are two ways to shift the graph, EG graph. So one way was to, of course, if I keep on increasing my R3, this slope will increase. If I reduce my speed, what will happen? If I reduce my speed, if speed is reduced, then what will happen in the, basically what is my E? E is proportional to N, right? So EG will reduce. EG will reduce. So if EG reduces, what will happen? The graph will shift downwards, right? Generated voltage will shift downwards. So if I copy this graph again, instead of the slope, like although my resistance is some value, it is less than the critical resistance, but the graph will shift down. So if the graph shifts down, voltage buildup will again fail. Again, deleting this will be very mundane task for me. Okay, so if I keep on reducing, so let me just draw, okay, let me just draw a single line only. This will be easier actually. Can I draw a single line? I don't know. Okay, so graph is somewhat like this. So if I can group it, let me group it. Okay, so now if basically I'm changing the speed, I'm lowering the speed, what will happen? This EG graph will shift down, right? So this will shift down, this will shift down, and after a certain stage, like let me make it more slopey, because that will be easier for me to explain. Yeah, like this is fine. Yeah. So again, if I duplicate this, after a certain point, what will happen? It will reach the tangent, right? As soon as it reaches the tangent, let me change the color here. Let me change it to something else. Okay, not this. Where are the colors? Where are all the colors? Let me change it to pink. Okay, what is happening? Why both the colors are changing? Okay, both colors are changing, huh? Okay, both of them are, okay, that is the problem. No, both of them are getting grouped actually. Okay, that is the problem. Not add to library group, don't add to library. Already library has so many things. How do I, yeah, remove this? Yeah, okay, so let me color this thing. Yeah, this will work. So what is happening here, right? Basically the speed is reducing. So there will come a certain point where this, although I am not varying the resistance, and initially for a certain speed the RSH was not tangent, it was totally fine, there was voltage buildup happening, but as I am reducing the speed, so graph will go down, and at a certain point automatically the RSH will become tangent to, will become tangent to, the basically EG graph. RSH will become tangent to EG. Okay, so that is the case over here. I hope you have understood. So that's why it is written here, if the minimum speed at which the voltage generator builds up for a given resistance. Okay, if I keep on reducing my speed, the open circuit characteristics will shift down, and there will not be any intersection, and if there is no intersection, voltage buildup will fade. So that is what we will discuss, that what can be the causes of failure of voltage buildup. So the first cause will be if there is zero residual magnetism. If I assume my core to have no residual magnetism, that means what? My E residual also will be zero. If my E residual is zero, simply there will not be any field current. So of course voltage buildup process will not start. So that was our assumption, that there is some residual magnetism, right? Without that, it is not possible for the current to flow, for the current to increase, right? And voltage buildup process to start. So initially what we can do, we can connect an external DC supply to the field winding, which can initially magnetize the core, which due to which there will be some residual flux in the core. That is one of the remedy of zero residual magnetism. Now second one is if I have connected my field polarity opposite, right? If let's say the orientation is wrong, so if let's say in this case, what is the direction of the magnetic field? Along the, okay, this is along the, this should be coming out here. Okay, sorry. This direction is along the right hand side, right? For the first one, okay, simple right hand rule, I can see this is along the right hand direction, and for the bottom one, it is along the left hand direction. Okay, this is also, okay, what mistake I made. This will be going down here, not here. If I have, okay, let me just copy. Okay, this is same only. Let me change the direction. I have changed the direction, right? So this direction is changed. So previously, if you see that the direction of the flux was on the right hand side, and now the direction of the flux is on the left hand side for the bottom diagram. So if I assume my residual flux to be in this direction, right? If I assume initially the residual flux is in this direction, for this case as well, of course, the residual flux direction will not change. Now, what is the problem if the developed flux and the residual flux are in opposite direction? So initially there was no current, due to that there was some residual flux, due to residual flux there was some generated voltage, due to that EG some field current flows. Now if some field current flows and if the terminals are connected in opposite manner, right? How can it be connected in opposite manner? I will show you. So if I copy this circuit, yeah, this circuit only I will copy. So this is the circuit 1, and in the circuit 2 what I can do, is I can simply interchange these things. Interchange these things. Okay, so what will happen basically here is this, okay, sorry, what am I doing, this will be connected here, right? And this will be connected here. So ultimately, right, the field current direction will be along the coil, will be in this left hand side direction, and here it was on the right hand side, right? So the flux line also will change, flux direction also will change. If the flux direction changes, so if there is some current, right, it will further reduce the overall flux, right? Because previously if my residual flux was there and due to that some IF current was flowing, so what was happening, my phi dash was equals to the phi total was equals to phi residual plus the phi dash additional. But now as they are connected in opposing polarity, it is just like acting like a differentially compounded machine. So due to some phi residual, some IF current will flow. Due to that, overall flux will be now phi residual minus phi dash. So overall flux is reducing. If overall flux is reducing. So my field current will further field voltage, sorry, the generator voltage will reduce. The voltage buildup is failing up. It is acting like a negative feedback system. So voltage buildup will simply fail. So how can I combat this? Simply reverse the field connection. If I reverse the connections, F1 and F2, that will work. So that's how we can eliminate the subtracting polarity. Okay. So if, like, simple way to test the polarity, if the machine fails to build up the voltage, just swap the field terminals and that will help in generating the voltage. Same reason, if the rotation of the prime mover is in the wrong direction, again whatever is the induced EMF, that will oppose the initial flux. So this time the EG, because EG is equals to phi ZNP by 60A. So basically, if speed is negative, it is in opposite direction. So what will happen? EG will be negative. If EG is negative, then my IF also will be negative, because it is basically E residual EG divided by RSS roughly, right? So basically IF will be negative. If IF is negative, then my flux is in the opposite direction. If flux is in the opposite direction, that means overall flux, right? Overall flux will be initial phi residual. Again, it will be opposing. So that's why overall flux will reduce. So voltage buildup will again fail. Okay, very easy and simple to understand, right? So I hope you have understood this basic point, that we cannot rotate it in the opposite direction. So if we are rotating in the opposite direction, that again if you change the field terminals, right? Again if you change the field terminal direction, again it will work. So remedy, ensure the prime mover rotates in the correct direction, or you can swap. Again we can swap F1 and F2. As both of them are swapped, both of them will be negative, so both of them will aid each other. So again voltage buildup will occur. So we can swap F1 and F2. Okay. So next thing, again we have discussed that excessive field resistance. This has already been discussed here, right? Already has been discussed here. So I don't feel I have to explain here much. So of course our shunt resistance must be lower than the critical resistance, otherwise voltage buildup will fail, right? What is the maximum value? Maximum value will be the case where the shunt resistance or the field resistance will be tangent to the open circuit characteristics. Okay, and if it's low speed of the prime mover, if the prime mover is lower speed, of course the developed voltage waveform will shift down. Again the shunt resistance automatically will become tangent due to the developed voltage waveform shifting down. So again voltage buildup will fail basically. Okay, so same thing. So these are the conditions basically for proper voltage buildup, and graphically I hope you have understood what is happening. So I want you to try out these questions by yourself, and then I will come back with the solutions, because I have explained a lot of things here. So I want you to use your brain and try these questions out. So these two questions, these 3-4 questions, I want you to try it out by yourself. Then I will come back with the solutions. This is the second one, this is the third one, and I think that's it. Yeah, that's it basically. Yeah, after that we will discuss about the load characteristics, right? Yeah, load characteristics only we will discuss. So yeah, these 3 questions you try it out. Let's solve this question. The open circuit characteristics of a DC machine rotating at 800 rpm is shown below. The field current and the voltages are shown below. So basically what we do, when we like in the lab, you will perform the experiment, that in the lab if you go and if you want to test your DC machine, right, if you want to characterize your DC machine, you will perform this experiment where you will measure the voltage across the armature when the generator is open circuited, and also you will measure the field current, right, as I have shown you the circuit diagram, right, and then you will plot the graph, and from there you can ultimately draw the open circuit characteristics of the machine, of the DC machine, correct. So here they are telling me that for zero field current I have some residual voltage, that is this residual voltage, and slowly it is increasing. If the field current is increasing, the voltage is slowly increasing, and roughly you will get a curve like this. Okay, so what is the important portion? First they are asking you, determine the critical field resistance at 800 rpm and 600 rpm. What is the critical field resistance at 800 rpm and 600 rpm? So how will you determine this? So for you to determine this, roughly, right, your graph, you have to approximate it to a straight line in this region. In the middle region, roughly it will be like straight line, because if you see here, right, it is almost in the saturation. So here, right, if you see, almost delta I is 2 amperes, but the delta V is only 20 volts. But here if you see, again delta I is less than 2 amperes, but you see how huge there is voltage difference, 40 volt of difference, right? So we will choose the linear region. So this region will be approximately linear. The middle region will be approximately the linear region. They should have actually mentioned which one is the linear region. This region, right, the middle region will be approximately the linear region. Okay, so this region. So how do I find out the critical resistance? Critical resistance is basically the slope of this graph, right? So if I just find out the slope somewhere here, because this is the linear region, then that will be my critical resistance for speed of 800 rpm. Okay, so how do I find out the slope of this graph? Slope of this graph will be delta into Eg divided by delta into If. Okay, so delta Eg, like I can choose this portion, right? Delta Eg is, what is the delta Eg? 120. Okay, I know, I do agree. Actually, the question is completely not correct. They should have mentioned like what is the linear region and stuff. So I'm assuming this to be the linear region. So if I assume this to be the linear region, what is the delta Eg? Delta Eg is 40 volts divided by delta If. Delta If is 0.25, right? 0.25. So this will come out to be 160 ohms. Okay, so 160 ohms is the critical resistance in the case 1 where my speed is 800 rpm. Now what will happen if the speed has been reduced to 600 rpm? So we know that our speed is proportional to phi ZNP upon phi, like it is directly proportional to speed, right? Sorry, our induced EMF or generated EMF is proportional to the speed. So Eg1 by Eg2 will be N1 by N2. So basically, right, this numerator delta Eg also will be multiplied with N1 by N2. That's it. Sorry, N2 by N1, because my Eg2 will be what? Eg2 will be Eg1 into N2 by N1. So delta Eg2 will be equals to delta Eg1 into N2 divided by N1. So very simple, same thing we will do. So basically our formula will be this, right? It will be delta, like the critical resistance will be delta Eg2 upon delta If. So field current change will not change, right? So now this will be equals to what? This will be delta Eg1 divided by delta If into N2 divided by N1, right? And what is this value? This value we have computed as 160 ohms. So this will be 160 into N2 divided by N1. So the new speed is 600 rpm and the old speed is 800 rpm. Okay, so this value will be 5, so 120 ohms. So the critical resistance will now reduce because the speed has reduced. So if the speed is reduced, so the critical resistance automatically will reduce. For now, for lower value of RSH, the shunt machine will fail to develop EMF, right? So that's why we don't reduce the speed. Okay, so I hope you have understood this very basic point. Okay, so yeah, that's basically it. Okay, that's basically it. Now what is the second portion? Second portion, if the field winding resistance is 55 ohms, find the range of the rheostat to vary the terminal voltage from 200 to 250 volt at 800 rpm at no load. So this was the part A basically. Now the part B, what are they telling in part B? So here, right, they have mentioned that the field resistance is 55 ohms. So what is the basically field current given us? So if it is open circuit, that means basically I will have the field winding here and the field resistance is 55 ohms, and there is this RA that they have not given me, and the DC machine is here, right, that will develop basically a EG voltage, correct, and it is open low circuit because zero current is flowing. Whatever current is flowing out of the armature, same current will flow through the field windings. Okay, so yeah, same current is flowing through the field windings. now 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 the important portion is if my IF will be equals to what? IF will be equals to EG by RA plus capital RF. If I assume, because RA is not given to me, generally RA is very lower than the field resistance. So RF will be very large than small RA. RF will be very larger than small RA. So roughly I can write my field current to be equals to EG divided by capital RF. Okay. So the important, like, what do I want to come? So I want to see which point actually satisfies this equation, because all these are steady state value voltages, right? I have to see which point satisfies this equation. That is, what is the equation? Equation is IF equals to EG by RF. So I have to see which point from the characteristics satisfy this equation. Okay. So if I observe, like, I have to just I have to put and plug in values, right? So here the important point to note here, 200 voltage is already there, right? 200 voltage is already there. So ultimately what we have to do is, I know 200 voltage is there. That will be the terminal voltage almost, because if I assume that the RA is very small, so the drop also will be very small. Okay, so that's why you have neglected. So 200 I know. What is the RF value, right? So IF I know, at 200 volt I know what is the field current. 200 volts, the field current is 1.75. So what will be the RF? So RF will be equals to 200 divided by 1.75. So this value will come out to be 200 divided by 1.75. This value will be 114.28. But currently what is the resistance? They have told me that the field resistance is 55 ohms. But actually, to satisfy, to generate 200 volts at the output, right, approximately, the resistance should have been 114.28 ohms. So this value will be equals to the external resistance plus the shunt resistance that is already present in the circuit due to the field winding. So external resistance will be R external will be 114 minus 55. So this value will be 59.28 ohms. Okay, 59.28 ohms. Now this is the case one, right? Now what are they telling? They're telling me that I want my terminal voltage to be 250 also, right? So here, right, I don't see a 250. So what I can do, again, I have to do bit of approximation. So my curve, right, again I have to assume it to be linear here, although it is almost saturating, but I have to unfortunately assume it to be almost linear. In this region it is approximately, I will assume region linear. So I will find the slope here, and from the point slope format I will be able to find out the voltage 250 volt. What do I mean by it? So first of all, in this region, right, I will find out the slope here. Okay, in this region, what will be the slope? This region, what will be the slope? So if I copy this graph, like ultimately what I want to say is that I want to extrapolate. So ultimately what I need to find out. So let's say this is the point. This is one point. That is the value of the terminal. That is what do you call the voltage is 260 volts. Okay, 260 volts, and this value, let's say, is the point of 240 ohms, right, 40 volts. So this is the current. What is the current here? Current here is field current here is 3.15 and 5 amperes. So this will be 3.15 and 5 amperes. So if I approximately find out the slope here, slope of this graph, if I assume this to be almost approximately linear, what I can do, somewhere here, right, somewhere here, although it will not be exactly, somewhere here this point will be, if I know the slope, because I will be able to find out the equation of the line, this point will be the point of 250 volts. That is what I want, right? So we have to do a bit of approximation. So what is the slope in this region? Right, slope in this region, again, delta Eg divided by delta If, that is equals to delta Eg will be 20 volts divided by delta If. Delta If will be 1.85 amperes. Okay, so 1.85 amperes. So this value delta Eg is what? 20 divided by 1.85. This is 10.81 ohms basically, or I'm not writing the units here. So I know the slope, I know a point. What is the point? Point is 240 comma 3.15. It is just simply a point slope format, right? So I can write down the equation of the line. So my Eg will be equals to slope, that is 10.81 into If, plus I have to satisfy the point as well, right? Okay. So I can write the point slope format. So it will be Eg minus 240 divided by del If. So it will be If minus 3. I'm just using the point slope format. I hope you know how to write the equation of a line. So this will be equals to 10.81. So from here I can write down the expression of Eg. So expression of Eg will be equals to basically this value, right? So 240, sorry, this will be 10.81. So ultimately, right, ultimately what I want to find out, I know Eg. So like what have they told me, they want to vary from 200 volt to 250 volt. So I will replace here Eg with 250 volts. Okay, so what will be the value of current then? What will be the value of the field current? So this will be 250 minus 240 divided by If. I don't know the value of field current, minus 3.1 equals to 10.81, right? So from here I can directly say this into 10 plus 3.15. So this is like If. From here If comes out to be 4.07 amperes. Now from here I can directly say the resistance. what is the field resistance? Again, they have to satisfy this equation. It should be equals to Eg divided by If, right? So this will be equals to Eg divided by If. So Eg is 250 volts, If is 4.075. So this into 250, this will be 61.35, okay, ohms. But actually, what is the field resistance? Field resistance are it, this should be equals to the external resistance plus the RSH, the shunt resistance, right? So from here I can find out the external resistance to be equals to 61 minus 55, right? 55 was the shunt resistance. So from here I can directly say it will be equals to 6.35 ohms. Okay, so basically I will vary my external resistance from 6.35 ohms, 6.35 ohms to 59.28 ohms. So this will be the range of the external resistance. So 59.28 ohms, 59.28 ohms. So this question is actually pretty elegant. We are not using simple KVL cases, right? We are using the graph to understand each and every specific thing. So the third question, right, actually is wrong. I should not have been included. I just remember now. This was supposed to be a different question. So third question is wrong. Okay, this is not okay. Sorry, this third question is kind of wrong. This we will discuss when a load could be connected. So ignore the third question for now. So yeah, let's start with the next question. So a shunt generator has a critical resistance of 200 ohms at 800 rpm. If the speed increases to 1000 rpm, how will the critical resistance change? So I have increased the speed. So the flux induced EMF line will shift upwards. So Eg will go upwards basically. So if Eg goes upwards, then I will have more range of critical resistance. So critical resistance also will go higher, because in the previous question only I have derived that your critical resistance, right, R critical dash will be equals to del Eg, that initial critical resistance, into the n dash upon n, like the new speed upon the old speed. So I can write here R critic new n new upon n old into R old. So I'm not telling you to remember the formula, I have derived it. Okay, you can understand it conceptually as well, right, how it comes out. So this will be R new. Okay, so this value, right, so the old critical resistance is 200 ohms, so it will increase basically into the new speed. New speed is 1000 divided by the old speed is 800. Okay, so by 4 to 50 ohms. So critical resistance will increase by 50 ohms, so increases to 250 ohms. Option C will be the correct answer in this case. Okay, let's read the next one. If a generator fails to build up voltage, which of the following is least likely to be the cause? Imperfect or poor brush contact. So if there is poor brush contact, there will be more brush drop, VBD will increase. So of course the residual voltage will not be enough to nullify this voltage. So yeah, this is a valid cause. Field resistance, which one is this is least likely? Field resistance is lower than the critical resistance. No, if field resistance is lower than the critical resistance, then there is no problem, right? If RF is less than the critical resistance, then there is no problem. If the field resistance is higher than the critical resistance, then the voltage buildup fails. So in this case, voltage buildup will happen. So this is of course the correct answer in this case, because this is the least likely that can cause the voltage buildup to not happen, right? But let's read the other options. No residual magnetism. So again, of course, if there is no residual magnetism, of course there will be problem in voltage buildup. incorrect shunt connections that weakens the residual magnetism. Again, incorrect field polarity, this also we have discussed, right? So only option B is correct, because if the field resistance is lower than the critical resistance, then of course voltage buildup will happen. It is not like voltage buildup will not happen. Okay, so yeah, I hope you have understood this point. Now let's discuss the load characteristics of DC shunt generator. What will happen in case of a DC shunt generator, right? So let me bring back the previous graph, this graph. One graph I had, right? This graph only, I guess this is the graph. So if I bring back, right, this graph, okay, and we are discussing about the load characteristics now. Okay, the load characteristics. Let me draw the critical, like, shunt resistance value, like this. Yeah, so we are discussing about the load characteristics. Okay, so in case of load characteristics, what can I say? So I can say here that what will happen basically. So if I connect my DC shunt generator to a load, what will happen? So now my load current is not equal to 0, right? So let me write down the equations. Okay, so what is the armature current now equals to? Armature current is equals to both the load current plus IF, right? Okay, so here, right, although in the separately excited, I told you we keep the field constant, but here, right, I may not be able to keep the field constant. Why? I will explain. So let's say if the load current increases, because of course I am varying my load. So if I am increasing my load IL, right, if my IL is increasing, of course the armature current has to increase, otherwise who will provide that extra current? So IA has to increase, right? IA has to increase. If IA increases, what will happen? If IA increases, the armature reaction will increase, because I have increased the load. So armature reaction will increase. If armature reaction increases, what will happen? The field, main field, right, resultant field will decrease. If the resultant field decreases, what will happen? The induced EMF reduces, because induced EMF is proportional to the resultant field. If induced EMF reduces, so voltage will reduce, right? Voltage equals to what? E minus IA RA. So voltage will reduce both due to the EG reducing, as well as, of course, if IA is increasing, of course this is in subtraction. Due to this also, the voltage will further reduce. So voltage is further getting reduced. Now one more thing, if the terminal voltage is reducing, there will be a positive feedback. I will discuss about that. So terminal voltage reduces slightly, right? So ultimately, if I want to draw the no load characteristics, so what is happening with increase in load? If I assume with increase in load, right? With increase in load, like this, let's say this is the voltage, open circuit voltage, when no load was connected, right? When no load was connected, so what I can do is I can plot these two graphs together. Okay, so this is the graph of the open circuit in when no load was connected, right? So if no load was connected, this will be the steady state value, correct? This will be the steady state value. So I will just plot this here. Okay, so let's assume that this is the like steady state voltage, V steady state or Vs for this particular shunt resistance RF. Okay, so at no load, this is the load current, this is the terminal voltage. At no load, when the no load is not there, this is the steady state voltage, that is Vs. Okay, now as the load is increased, what have I discussed, that the load current will increase, armature current will increase, so the armature reaction will be more, there will be more drop due to IRA, and of course due to the generated EMF reducing, right? So what will happen, the voltage waveform will be somewhat like this, it will slightly reduce, right? It will not follow the straight line, it will slightly, if IA is increasing, it will reduce from Vs, the no load voltage Vs, right? It will reduce. It will reduce. After a certain point, what will happen, there will be a point of inflection. So here, right, the current will be maximum here. Why here the current will be maximum? This will be the IL maximum current that the generator can take. After that, there will be huge sharp drop. Why there will be sharp drop? I will discuss about this. So one thing I am noticing that here, okay, IL is increasing, IA is increasing, armature reaction is increasing, so flux will reduce, so E will reduce, so EG, IA both will reduce. So what is happening is this reduction is in terminal voltage. Initially we will feel that this reduction in terminal voltage is not much. So what is the field current? So field current IF, field current IF is equals to V upon the shunt resistance. So I assume initially, because of course initially also V is reducing, but IF will it reduce? So I will tell that initially the reduction in IF is low, as can be seen from here, right? As reduction in Vs is low, so IF also reduction is low. But after IL max, the field current reduces sharply. So if the field current reduces sharply, then the flux further reduces, then the voltage further reduces. If the voltage reduces, then the EG voltage is equals to what? Sorry, EG further reduces, then the terminal voltage further reduces, and this becomes a like a positive feedback in the opposite direction. That is, the voltage is trying to go to zero. So this becomes a positive feedback, positive feedback in opposite direction. So voltage will keep on reducing. It cannot go obviously negative. It will sharply reduce. It cannot go negative, and after certain point it will go to zero. So this value is what? This basically means that the Vs is zero, right? Basically the output is short circuit. If the output is short circuit, this is the value of the current that the device or the generator will take. If I short circuit the output, this is the value of current, right? So basically this is the circuit in the short circuit condition. So I have a field winding here, right? I have an armature resistance here, I have this generator, this is Ra, this is Vt. This is R SH. Okay, so if the output is short circuited, it basically means what? If the output is short circuited, that means here the voltage is 0. If the voltage here is 0, that means here the current is 0. So it basically is the condition where the field current is 0. If IF is 0, what is the induced voltage? If IF is 0, if IF is 0, the EG is what? It is simply the residual voltage. So here the generated voltage will be E residual, right? What is the current? Because here the current is 0. So what is the current here? The current through the armature that will flow through this, that is a short circuit current, ISC. Full current will flow through this loop only. None of the current will flow through here because IF here is 0. So ISC will be equals to E residual upon armature resistance RA. So very important, right? Whenever the characteristics is given, very important to understand what does each point mean. Okay, so here your ISC will be equals to E residual by RF. So one day they will give you a question where they will ask you to find out the residual voltage if the this load characteristics is given. Okay, so if this load characteristics is given, what will be the residual voltage, and if the armature resistance also is given. So this ISC short circuit current will be equals to E residual by RA. Very important to understand the load characteristics. Okay, okay, I hope you have understood this basic point. Okay, so this is the graph, basically this is the load characteristics. So in response to this, right, what we can do, we can actually E residual. So E residual, E residual, this is the terminal voltage will be 0. Yeah, that's fine. Yeah, that's it basically. So that's how you will be able to find out the E residual voltage if, let's say, you haven't given the graph and this value also you have given and RA also you have given, right? So E residual will be ISC into RA. Okay, very important, and this will be the IL max, maximum value of the load current. So I can obviously find out what is the maximum value of the load current corresponding to this EG, right? So this also I can track back. Okay, if they give me the information, I will be able to track back this value. Okay, okay, I hope you have understood. So one more thing, one more important thing that you must understand, that here, right, this is the current, this is the voltage, right, terminal voltage. So terminal voltage is here. So this value, right, okay, just hold on. If my voltage is here, so this value is what? This value is basically the drop, right? This value is basically the drop, that is the drop in the armature resistance and the drop due to the armature reaction. So this is basically the drop due to the armature resistance and the armature reaction, correct? So this is basically the drop. Why this is the drop? Basically because here, so basically, right, like how did I find out this value? This value was, that is my IF was equals to, I have assumed it to be VT by V by RF, right? But of course my V is not exactly equals to EG. So V is equals to what? V is equals to EG minus IARA, right? So EG will be equals to what? EG will be V plus IRA. So this value is V divided by RF, and additional, if I multiply RA here, RF here, sorry, okay, this is, so this is my V, right? So this V is here. So this point is the V point. This point, let's say, is the V point. If I add IARA with this value, I will get EG. Correct? I have to add this additional value IARA, I will get EG. So this much amount of drop is known as, if this length is given, right, this length is actually equals to, this length is equals to IARA. Okay, another important point. So I will highlight the important points. So this length will be, because this point is the V point, right? This point is the V point because this is V equals to IF into RF. Now if I add IRA here, I will get back EG. EG is this magnetization curve, right? So I will highlight the important points. These are very, very important. This can be asked in exam. This is the one point that is important, and this is the other point, right? Generally, everywhere, most people will skip this, right? Most people will skip this. They will not explain this properly. Okay. So yeah, I hope you have understood this basic point. Okay. So yeah, that was basically it. That is what we wanted to uh, discuss. Okay. So yeah, now like whatever I have discussed, the same thing is written over here. So let me delete these pages. That load characteristics, this characteristics show the terminal voltage changes with increasing load current. So I have not shown you the internal characteristics. This, that is the homework for you, that I hope you can do, right? Just simply, it is simply Vt by Vt instead of Eg. So there will be an additional drop of IARA. That's it. The graph will just shift down. That's it. Okay. So as load increases, armature current will increase. This leads to increased armature reaction and IARA drop. So the voltage also will reduce. So this will be the graph basically. Okay. And mostly always try to draw together the open circuit characteristics and the load characteristics, because they synergize very well together. Okay. They synergize very well together. Okay. So behavior, initially the drop is small, after a certain point often greater than 125% of the rated load, armature reaction becomes severe because armature reaction is very high, and there will be a sharp drop and it will bend backwards from point A to B. So here it will be point A, this will be point B. So this characteristics is known as the drooping characteristics. So this characteristics, the load characteristics, is known as the drooping characteristics. Okay. So yeah, all those things are there. Of course here, right, additional brush drop is there. If armature current increases, the brush drop will also slightly increase. So all these drops are already included here. Okay. So I have just divided in three cases. So if in case of no load, it will be just like open circuit characteristics, whatever we have discussed. So we assume that the drop across the array is very small, as the IF current is very small, because IF becomes roughly IF equals to IA, and I know IF is very small, so RA into IA also roughly we assume it to be 0. So assumption is the V voltage is equals to EG. Okay. Under load, when IL is greater than 0, so there will be these three drops, due to which there will be gradual decrease in the voltage, and after a certain point there will be huge amount of decrease. So when this will go short circuit, this will go short circuit when at that point of time, whenever the output is short circuit, at that point of time only that means the field current is 0, and if the field current is 0, that means only what will be the voltage develop will be due to the residual flux, because speed is constant. So only phi residual is there, due to which E residual EMF will be induced. So current, short circuit current, will be I short will be equals to E residual divided by RA, according to this graph, right? Whatever we had discussed according to this graph. Okay. So we'll copy this graph again and I will paste this here. So these are the characteristics of this shunt field generator. Okay, generation. So these are the key points. So stable operating region is limited due to risk of voltage collapse under overload. So of course I cannot go beyond IL max. If I go anything beyond IL max, the voltage will sharply reduce, right? So stable operation is between 0. So IL can vary between 0 to IL max. I cannot go beyond IL max, else the generator will not operate stably. Okay. So here whatever we have discussed is like written over here. So this non-linear circuit behavior makes shunt generator self-limiting in current. They cannot supply large short circuit current, which can be beneficial for short circuit. So if let's say for some reason you short circuit, right? So if it, let's say it was a constant voltage source, right? let's say I have a constant voltage source, let's say I have a resistance, let's say this constant voltage source, it is supplying a resistance of 5 ohms. So maximum this whatever current this voltage source can support is 5 amperes. Okay, maximum. So I max here, it can support 5 amperes. So now if 5 ohms load is connected, so how much current is flowing? Currently the current is flow, whatever current is flowing, that is 1 amperes, right? If let's say I reduce the resistance, let's say this resistance now is 2 ohms, voltage is still 5 volts, what will be the current? Current here will be 2.5 amperes, right? If I further keep on reducing it, and let's say there is some sort of fault due to which the circuit becomes short circuit. If the circuit becomes short circuit, what is the current? Current here will be 5 divided by 0, which will go to infinity. So it goes to infinity, right? It goes to infinity. So if it goes to infinity, that basically means what? That basically means that the voltage source will be damaged, because it can only support maximum of 5 amperes of current. So but if I had a shunt DC generator here instead of this, what will happen? If I even short circuit it, what will be the short circuit current? It cannot go beyond a certain value. The short circuit current for a generator, DC shunt generator, the short, it will just simply be self protecting. It will not go higher current, it will just limit its current to E residual upon R upon RA, right? So that is the advantage of DC generator. Okay, it behaves as a non-linear feedback. Okay, so maximum load current, how can you determine the maximum load current, right? So to determine the maximum load current, the generator can safely deliver, extend the parallel line to the field resistance line on the OCC plot. Uh, the OCC marks the line beyond which multiple intersection points may cause instability. Determine the armature current given. Okay, extend the line parallel to the field resistance line on the open circuit. Okay, the tangent point on the OCC marks the limit beyond. Okay, okay. Yeah, basically what they're telling is, so which we already have done, basically, that here I have the load characteristics, right? And here I have the no load characteristics. So like basically what are they saying? They're saying the same thing only, whatever we have done here, right? We extend this point to the open circuit characteristics on the RF, right? On this field resistance slope, and then we add the extra additional drop, okay? And that gives us the maximum voltage, like save operating voltage at maximum load current, right? Or directly you can find it from here as well, that also works. Okay, okay, maximum current that the armature can support. Actually we have to find out the maximum current that the armature can support, right? Okay, okay, so this, right, this is IA into RA. So basically assumption is field current is almost constant. If the field current is almost constant, I can say that IA is equals to IL plus IA. So when IL plus IF, so when my IL will be maximum, so the armature current also will be maximum, right? So IL will be maximum, then my armature current also will be maximum. Plus the field current. Okay, so if my load current is maximum, then the armature current also will be maximum, right? If you want to find out the maximum armature current, what you will do, you will first extend this point, connect it here, because this is the point only where the voltage can be the highest. After this, sorry, this is the point only where the current can be highest. After this, right, what happens? Due to the positive feedback, the voltage further reduces, drooping characteristics. So this is the maximum point. This I will extend to the open circuit line. This I will connect here, and from here, this is the point of voltage, because this is the basically point of the field voltage V by RF, and V is V additional added with IRA will give me the generated EMF. So this, right, if I am able to find this point and I know this point, the difference of these two points will give me the IARA max. So this will be the IARA max, IA max into RA. right? This will be Ia max into Ra. Okay. So graphically, this is how you can identify your safe operating regions and all those things. That is what they're telling you. The armature current corresponding to this gives the maximum current. So this is the maximum load current, but what if you want to find out the maximum armature current? This is how you can find out the maximum armature current. So the difference between these 2 points, right? Let me write this value. Let me write this. Let's write this as y1, and let me write this as y2. So y1 minus y2 is equals to Ia max into Ra. So Ia max will be equals to y1 minus y2 divided by Ra. Okay, so this is also another very important point in the graph. Okay, so I hope you have understood this basic point. So these are the comparisons. Basically, you can see and go through this comparison. I don't want to go through it over again. Okay, so this is it basically for this lecture, and in the next lecture we will do few questions on this, whatever we discuss. Also, we will try to finish off with DC series generator and DC compound generator, the characteristics of DC series and compound generator. Thank you for watching, and I will see you in the next lecture. Until then, happy learning, and please make sure to comment on the first video, because trust me, whatever I have taught you in this lecture, right, you cannot find anywhere. Just trust me on that. You can go and search anywhere on YouTube or any paid course, you will not be able to find it out. So I hope you enjoyed this lecture, and I will see you in the next lecture. Until then, happy learning.